Good morning, everyone. My name is Dheeraj, and I welcome you all to CPP India community. Thank you for joining today's session. Before we'll start, I will just give you a brief about this community. The aim of this community is to bring people together who have similar interest in learning and expanding their knowledge about C++, and also provide them the platform to discuss, share, and showcase their work done primarily in C++. So as always, I will take a few minutes to give you some important information about how you can interact with the community. You can interact with our community by joining our Discord channel. You might have already received a link, and if not, please register. You will get a link. And if you are facing any problem, please contact me or any of the admin or moderators of our community, or you can reply to CPP India email ID. So that's fine. We will connect with you. And we will be recording this session, and post this session, this recording will be uploaded to our YouTube channel. So please subscribe to our YouTube channel to get the notification whenever it will be updated. And join our Discord channel, because in our Discord channel we used to announce all our session information first on Discord channel only, and then we go to other platforms. So to be updated about the community, whatever happening in community, please join there. And you can ask questions in our Discord channel, and you can discuss there. We used to send some questions there for discussion, so you can enjoy those also. And post this session, we'll share one feedback form. So please spare some time and give valuable feedback about this session. So now that's all about the community in introduction from my side. Now I will welcome Tsung-Wei to this community. He is in his time zone, it's almost a midnight, and he found time for us. So thank you, Tsung-Wei. And I will call you to come and introduce yourself, because you'll be the best person for this.
Absolutely.
Yeah, so over to you, Tsung-Wei.
Could you please stop sharing so I can?
Yes.
Yeah. All right, give me a second. All right, I assume everybody can see the slide. All right, hi, I'm from the University of Utah, and it's really my pleasure to share with you today the Taskflow project. And as a university faculty member, my research focus on making parallel computing easier to handle, so you can quickly boost your application performance. Today, I'm very excited to show you Taskflow. It's an open source C++ programming system that can help you quickly write parallel and heterogeneous programs. You probably already know parallel computing is critical to advance your application performance. For example, if you look at this chart, a single-threaded machine learning program can take several hours to finish, but it can be reduced to only a few minutes or even a few seconds if we are able to run it in parallel. That's the power of parallel computing. By leveraging many core processing units, we are able to speed up the performance by several orders of magnitude. And especially for today's hardware, if you have your laptop, smartphone, electronic device, they usually come with many processing units we can leverage. However, writing a good parallel program is very challenging because you need to deal with many difficult technical details, such as standard concurrency control, task dependencies, scheduling, data arrays, avoiding multiple processing units raised on the same data. And many CPP developers have a hard time in getting them right. especially for those who do not have that much experience in parallel computing. So the Taskflow project is trying to offer the solution to this, and we address the following question. How can we make it easy for C++ developer to quickly write parallel heterogeneous program with high performance and simultaneous hyperparameter? By high performance, we mean the program has to run fast and scale to many core computations. In CPU and GPU, by high productivity, we reduce the time it takes to implement the program. So let's take a look at Hello World example in Taskflow. Suppose we want to do 4 things, A, B, C, D, each representing a function or a task. A has to run before B and C. D has to run after B and C. So in this diagram, when A finishes, both B and C can run in parallel, right? When both B and C finish, D can start. So this is the dependency graph that describes this simple graph of 4 tasks and 4 dependencies. In terms of CPP code in Taskflow, this is how it looks in Taskflow. Only 15 lines of code to get a parallel task execution. And this is all you need. You create a Taskflow object to manage a task dependency graph. And then you create an executor that manages a set of worker threads to run Taskflow. And here we use the method in place to create 4 tasks in terms of C++ lambda and assign them to A, B, C, D using structure binding in C++ 17. To build up a dependency, we use precede, the method precede, to force A to run before B and C, and D, the succeed method, to force D to run after B and C. Finally, once we finish the description of this Taskflow graph, and we submit this Taskflow to the executor by calling the run method, and it returns a future, so we can wait on it to finish. At this moment, I believe many of you can fully understand what this code is doing, even though you are not an expert in parallel computing, because by looking at this code, it's transparent, it explains itself. There is nothing to do with any threading detail. You don't need to create a thread manually or manage those concurrency details. All you need is to focus on application level development to describe your program in terms of task dependency graph and throw it into our scheduler, and our scheduler will do all this parallelization for you. So here is how I'm going to do in the rest of the talk. I'm going to show you how to express the parallelism in the right way by starting with the motivation behind Taskflow and the application we target. Then I will present how to use Taskflow to parallelize your application and give you a rough idea about our work stealing scheduling algorithm. Next, I'm going to demonstrate some real use cases of Taskflow and show you how it can boost your application performance in large-scale parallel programs. Finally, I will share with you some of my experience in using C++ to parallelize some application so we can enhance C++ to make it more amenable to heterogeneous parallelism. Let's start with number 1. I'm going to show you the motivation behind Taskflow so you can express your parallelism in the right way depending on application. In the past, I've been developing parallel CAD software for VLSI system. And CAD stands for computer aided design. It is a software method to help people design integrated circuit or IC. You start from a high-level description of a hardware component that takes it to a CAD software. And the CAD tool, CAD software, generate a bunch of NANDs and synthesize them to the physical layout. And then you can tape out the layout to get a final chip that lives in almost all electronic devices today. And this is a seriously complicated process. For example, if you look at the layout generation process, it requires partitioning the graph of billions of nodes. Think about today's, if you have your smartphone, it has billions of transistors in a very tiny devices. So we cannot rely on human to design a chip. We have to write software program using algorithm to solve the chip design problem. And so we have to partition the graph of billions of nodes and then decide the location of this node, placing millions of cells in a very small area routing trillions of wires to establish the signal connection, and then analyze the timing of these billions of components. And the resulting task computational graph, in terms of encapsulated function code and task dependency, can easily go up to millions of tasks with cycle, dynamic control flow, and irregular computational pattern that takes several days to finish. Essentially, we want the answer to this question. How can we write an efficient C++ program, parallel program, for this monster computational task graph with millions of CPU and GPU dependent tasks along with algorithmic control flow? Because of building a parallel CAD tool is very complex, and we want to find a programming system that can assist us with the implementation and deployment of parallel algorithm. Otherwise, it's too difficult for us to manage all this concurrency and threading detail. To this end, we have invested a lot in existing parallel computing systems such as pthread, OpenMP, C++ thread, Intel TPP, SQL, StarPu, and law software from the Department of Energy in the US. And the problem is we found very few of them can meet our purpose. And the reason is as follows. We summarize two big problems of existing tool here in this slide. First of all, our problem defines very complex task dependencies. For example, analysis algorithm has to compute the circuit network of millions of nodes and dependencies. And the problem of the existing tool is they are often good at loop parallelism, but very weak in expressing this large-scale task dependency graph. On the second, our problem defines a very complex control flow. For example, if you optimize the chip layout, you write an optimization algorithm, you need to make essential use of dynamic control flow to implement various computational patterns to carry out, for example, combinatorial optimization or analytical method. And the problem is most of the existing tools require to describe a parallel workload in a directed acidic graph or a DAG. And this graph cannot have any cycle or conditional dependency. You have to describe the graph in one shot. The graph cannot have cycle. If the graph does not have cycle, that means you are not able to describe iterative workload. To better understand what these two problems are, let's take a look at an example of an iterative optimization program. So this program has 4 tasks, and it starts with the init task that initializes the data structure. And then it enters the optimizer task to perform some optimization. For example, we might solve a linear system using GPU. Next, it moves on to the converge task to check if the optimization routine converge. If yes, it goes to the output and stop, or otherwise it moves back to the optimization task again to iteratively solve the linear system, for example. If you can see the program has an iterative control flow. In doing this in a single-threaded setting totally makes sense. You can just write if-else to check whether the convergence condition evaluates to true. It totally makes sense in a single-threaded environment, but it's very difficult to do this in a parallel environment. Or maybe we should ask this question: how can we describe this workload of dynamic control flow? Right? Using the existing tools such as OpenMP or TPP or SQL or Cocos. What about a situation with millions of such tasks? And what about a way to describe them in end-to-end parallelism instead of partitioning the parallelism across a control flow? After several years of research, we arrived at a key conclusion. We need a new C++ parallel programming system. And the takeaway here is, while designing parallel algorithm is non-trivial, what makes parallel computing an enormous challenge is the infrastructure work of how to efficiently express dependent tasks along with algorithmic control flow, and schedule all these tasks across heterogeneous computing resources of CPU and GPU. That is the key motivation to support the Taskflow project. We want to strike a balance among 3 aspects: performance, productivity, and portability. We want to maximize the performance compared to the handcrafted solution. And we want to maximize the portability by leveraging the power of modern C++. More importantly, because writing a parallel program is very, very difficult, it's very challenging. So we want to maximize the productivity compared to handcrafted time. We want to reduce the time it takes for you to implement a parallel algorithm. We are not trying to replace any of the existing tools, but to address their limitation on task graph parallelism. And we keep our interfaces compatible as possible to reuse their facility. Because by doing this, we believe we can deliver complementary advantage to advanced C++ parallelism. Next, I'm going to show you how we can use Taskflow to describe parallelism using a task graph in your application. And again, Taskflow is a programming system, and I cannot present a programming system without showing you some real code. And I believe, this will not destroy your beautiful morning. And programming is quite subjective, so many arguments I'm going to present are based on my personal opinion. No offense, no criticism. It's all about C++ from both a users and researchers' perspective. In Taskflow, we have 5 task types: static tasks, dynamic tasks, CUDA flow tasks, condition tasks, and module tasks. Static task is the most basic task type in Taskflow. It takes a callable object and runs it. The dynamic task lets you define a task dependency graph during the execution of a task, so you can do parallelism dynamically. A CUDA flow task lets you describe a GPU workload in a task graph and offload that computation graph into a GPU. A condition task lets you integrate control flow into a task graph, so you can describe end-to-end parallelism. And the module task lets you compose a large task flow graph through smaller task flow. They are easier to optimize. In the Hello World example we have seen before, the 4 tasks, A, B, C, D, are static tasks. They are static tasks. They simply take 4 lambdas and run them. In most of applications, static tasks are quite enough. And you can use static tasks to describe pretty much 90% of the parallel application you need. The same Hello World example, but written in OpenMP's testing interface. And OpenMP is a language extension to describe parallelism using compiler directives. It is a very popular programming library. Almost all people start with to learn parallel programming. In this example, we use OpenMP OMP task syntax to create 4 tasks, A, B, C, D. And then we use the depend clause to specify the outgoing dependency and incoming dependency for each of the 4 tasks. For example, in task A, if you look at the graph, task A actually depends, both task B and C depends on task A. So in task A, we need 2 variables. We use 2 variables, AB and AC, to capture the constraint between A and B and the constraint between A and C. And we do the same thing for the other 3 tasks to describe this simple Hello World task flow graph. Well, the code is not very complicated, but it's static. But you need to explicitly define everything such that the compiler will know how to generate a dependency. So that means the order you write a task really matters, because you rely on compiler to generate the task dependency graph for you. So think about that. The problem is, if right now you switch to a different compiler, they need to disable OpenMP. Everything falls back to sequential execution. So the order you write a task has to be sequentially consistent with the sequential execution flow. And in many of the workloads, it's very difficult to make this happen because the dependencies come at the wrong time. And this makes it very difficult to describe upfront parallelism using OpenMP. Same example again, but written in Intel's Threading Building Block Library, or TBB for short. TBB is a general-purpose object-oriented parallel programming library in C++. It has been used in industry for many years. The idea of TBB is very similar to Taskflow in the sense it describes dependent tasks using a flow graph. And you create a flow graph, and then you use this monster template class of continue message and continue node to create 4 tasks, A, B, C, D. And you use this big template class continue message to relay the dependency between AB and AC and BD and CD. And finally, you need to identify the source task manually. In this case, it's task A, right, from your graph, and insert this source task into the scheduler, so the scheduler can start execution from there. According to our research, TPP has really excellent performance, and especially when you're running on Intel architecture, it really outperforms. But it turns out many of the API defined by TPP is very complex, even though they are very powerful. And I would say the drawback is mostly on the ease of use standpoint, in terms of simplicity and expressivity. And the final comparison is written in Cocos. And Cocos is another parallel computing library that recently received much attention from the community. It's also part of the exascale computing project under the Department of Energy in the US. Cocos leverages the C++ style future object to handle task parallelism. And as far as I know, at the time of this presentation, Cocos does not support C++ Lambda. So in order to create tasks, you have to define task functor or function object of fixed memory layout. For example, here we have a 4 struct, A, B, C, D, each representing a task in a task graph. And everything is based on C++ future object. You launch a task asynchronously and get a future, and then eventually hold the result to the task, and you relay the dependency between different futures. Once you finish the description of the task graph, you have to manually specify the scheduling detail. And because there are too many code, and I cannot finish all this presentation in one slide, so I will skip the scheduling part. Turns out Cocos is very powerful in describing this asynchronous task, but it's not very efficient in large task graph due to the overhead of many shared state control. And what I presented to you was my personal interpretation. It can be biased, so I took advantage of being a university faculty to give a programming assignment, asking students about 100 this question: how would you like to express this slightly more complex task graph of 10 tasks and 15 dependencies, and vote for the following 5 different libraries: Taskflow, OpenMP, TPP, Cocos, and StuThread. And I did not tell them I'm the author of Taskflow, otherwise all the students will vote for Taskflow. And what I'm trying to discover is how C++ learner, the first time learning parallel computing, what would they think about this parallel computing library, especially for those who are learning to use the parallelism in their application. This is how it looked. About 74% prefer to use Taskflow. And more importantly, based on our survey, the #1 concern most of the programmers have is my application is already complex. I want to parallelize it, I understand, because it boosts my application performance. But I don't like the parallel programming library to become another burden for me to learn to parallelize my application. This indeed is the goal we need to pursue. And we need to let developers focus on high-level algorithm as much as possible, instead of wrestling with many parallel tasking details. Any questions so far? I will make a post here. Good, let's move on. The previous example was static tasking. You decide a task to spawn at the first level of the graph. Taskflow can also do dynamic tasking. You can spawn a task dependency graph for the execution of the task using a dedicated interface, Subflow. In order to create a Subflow, you need to in place a lambda with an argument on Subflow, and then you can describe another task dependency graph in that Subflow. For example, here we create another task dependency graph for the execution of the task B. And the Subflow has 3 tasks: B1, B2, and B3, where B3 has to run after B1 and B2. So all the syntax you see from the Subflow are the same as the precede and succeed method we define for you to describe the task dependency graph. So when the scheduler, once you finish the description of this task flow graph, When the scheduler finishes A, it starts running B and C. And when it runs B, and it spawns another task dependency graph inside the subflow and start running B1 and B2 and then B3. Eventually, the subflow joins its parent task B, and then we move on to task D. And this is probably only 20 lines, less than 20 lines of code you need to write to describe this parallel task dependency graph. The subflow can be nested or recursive. You can create a subflow from another subflow and so on. And this is an example of a task graph that finds the 7 Fibonacci number using subflow. And we know the Fibonacci number is a series of a number where each number is the sum of the previous 2 numbers. And it can be done with the recursive parallelism. And this is the graph diagram that describes the 7 Fibonacci number in parallel. You can offload a task to GPU or graphic processing unit, which is particularly powerful for many matrix operation workload. And we manage this heterogeneous CPU and GPU tasking through the closure-based interface, CUDA flow. And the CUDA flow is a task associated with the CUDA graph, which is a new feature in NVIDIA since the CUDA 10. And for those who do not know what NVIDIA is, it is one of the biggest chip maker to produce the GPU. And GPU is very, very popular for today's artificial intelligence industry. If you look at this closure, a CUDA flow is very similar to the subflow. It takes an argument of a CUDA flow, and that will be created during the execution of that CUDA flow task. Within this CUDA flow, you describe multiple GPU work, such as data transfer. For example, you migrate the X and Y. In this case, I want to copy the data, X and Y, from CPU to GPU. And I use this copy method to specify 2 copy tasks, telling the CUDA flow, I want to copy some data from CPU to GPU. And then I have another kernel to define the kernel you want to run the computation on the GPU. In this case, we use a very simple 6CP, single precision vector operation as the kernel. Once the kernel finishes, we need to copy the result back from GPU to CPU. So we create another 2 copy tasks over here to copy X and Y from GPU to CPU. Apparently, if you look at the dependency, the kernel has to succeed, has to run after the copy task from CPU to GPU after that finishing. And before we can copy the result back to CPU, we have to wait until kernel finish, right? So this is how we describe a GPU workload in a GPU task graph. When you finish the description of the GPU task graph, you can pipeline the entire CUDA flow with the other CPU task or other CUDA flow. And this is very important because the CPU-GPU programming always involves some data transformation tasks at an expensive cost. For example, you want to transfer the data from CPU to GPU and vice versa. Without a suitable task graph interface, it is very difficult to express this overlap. And this design has 3 key motivations. So first, this closure-based enable the stateful interface. You can capture data in reference by using C++ Lambda to marshal data exchange between CPU and GPU tasks. This is very important for graph parallelism because when everything is formulated as a task dependency graph, we need to make sure the computation result of the CPU task is visible to GPU tasks and vice versa. Second, this closure interface can hide implementation detail judiciously. If you look at the code we showed you before, there is nothing to do with the GPU. You just need to tell the graph you want to copy data from CPU to GPU, and then copy launch the computation on the kernel, on the written kernel, and then specify another task to copy the data copy the result after the kernel computation from GPU to CPU. So this interface effectively abstract judiciously hide the implementation detail. And it can also be extended to new accelerator type. For example, we may have OpenCL flow or TPU flow or FPGA flow and so on and so forth. Conditional tasking is a powerful interface to enable dynamic control flow. And this is another task we define in Taskflow. And we believe this is one of the key features that stands out Taskflow from other library. You can create a condition task. You can create a condition task that returns a value indicating the next immediate successor or the next task to run. Of course, you must satisfy certain rule. You cannot jump anywhere you want. We do have a special scheduling policy for you to follow, which we'll explain later. Let's take a look at this example. In this example of iterative optimization we've seen before, I create a task graph of 4 tasks: init, optimizer, converge, and output. Init task initialize the data structure we need for optimization. Optimizer task launches the optimization routine, such as solving a linear system in a matrix form. And typically, this optimization algorithm is iterative. You have a bunch of iteration before you can go into the final converge status. And once the optimizer finishes an iteration, it moves on to a converge task. Let's check whether the optimization converge, right? And this converge task will return 0. When it returns 0, it goes to optimizer again, which means it hasn't converged. If it converges, it returns 1 and goes to output. And the converge task here is a condition task. It precedes 2 tasks. If you look at the code we wrote here, the converge task precedes 2 tasks. One optimizer, another one output. With this order, when it returns 0, the scheduler will ask you to optimize the task, or it moves on to the output. And we specify this in the return value of this task based on their dependency. And you can see in this example, there are ultimately only 4 tasks ever created during execution, even though it's iterative. You can describe this iterative workload in a whole graph entity. There is no need to partition your graph or synchronize it at each iteration. And this condition task can handle more complicated scenarios, for example, such as nested or non-deterministic control flow. In this example, I have a task graph of 5 nested cycles. Each green task is a condition task. It does nothing but flip a binary coin, next path. Either move on or go back. If the condition task returns 0, as we roll in the code here, return a random number, scale the random number from 0 to 1. If it returns 0, it moves on to the next task. Otherwise, it moves back to the first flip coin task. And there are 5 such tasks to flip a binary coin, so you can infer that the average number of condition tasks you need to go through before reaching the task end is 32. Because in each condition task, you got a probability of 1/2 for you to move on. So similar to the previous example, ultimately, we use only 5 condition tasks to model this nested, non-deterministic task execution, even though we may end up with a 32 execution averagely. The scheduler will reuse these 5 condition tasks. If we look at how existing framework handle condition, it's actually very problematic. We know many of them are based on direct acyclic graph, and they do not allow cycle. And I'm not talking about a cycle you have in a pipeline, but a generic interface for you to describe control flow in a parallel task graph. And the most common solution is to expand your task graph across fixed length iteration. For example, if you happen to know a loop condition, it's going to span 5 iterations. You can unroll your task graph by 5 times. And the result of that is increased graph size and memory consumption. But what about a loop of unknown iteration, like non-deterministic condition? Or some condition you may not know until some other condition happen, or nested condition. In fact, according to our research for generic condition, it's very difficult. There is no way for existing framework to describe generic condition, and they typically suffer from exponential growth of coding complexity. So that ends the condition task in Taskflow. And our task interface is composable. The next task type I'm going to show you is composable tasking. And this is a key element to improve programming productivity through composition. You can create multiple task flows, each representing a portion of your parallel decomposition strategy. That is easier to optimize at a smaller scale. Then you can assemble these task flows to form a large task flow that compose correctly and efficiently. In this example, we have two task flows, F1 and F2. F1 has two tasks, independent tasks, F1A and F1B. F2 has four tasks, F2A, F2B, F2C, and the module task composed of task flow F1. And you can do this composition in just one line of code using the method compose of. So here I create a task flow 1, and I in place two static tasks for F1A and F1B. And for task flow 2 F2, I in place three static tasks, F2A, F2B, F2C. And then I have another module task inserted into task flow F2 by using the method compose of. That means there is another task inside F2 that compose F1. And finally, I can use the same method precede and succeed to relate the dependency between different tasks. And for example, in this case, F2A, F2B precede the module task, and the module task precede the task F2C. And this is how composable tasking works. We can partition a large task flow project into several and smaller task flows, and each representing a particular parallel decomposition strategy. And you can see all the interface we have seen so far is unified, and that is the biggest advantage. The biggest advantage of Taskflow is everything is unified. You use the method in place to create a task, which can be either a static task, dynamic task, or condition task, and composition or cooldown flow. Then you use the single method precede or succeed to relay a dependency between tasks. And you can use all these syntaxes and idioms and API to create a really complex task graph that combines all these 5 task types and integrate control flow into your task flow, so everything runs end-to-end. And our schedule will then perform end-to-end optimization and to optimize the runtime, energy efficiency, and throughput. So you don't need to worry about all those scheduling details. You just need to focus on describing your application as a task flow graph. This is another example of using Taskflow to describe a k-mean clustering algorithm using CPU and GPU tasks. K-mean is a clustering algorithm that tries to find the best case centroid among a set of points. It is an iterative algorithm and typically have the CPU and GPU tasks running iteratively to compute the k clusters. Here we use only a single task flow to represent the entire k-means workload. So we have a one CUDA flow to perform the copy the data from CPU to GPU because we want to do some computation on GPU. So we need to prepare the data on CPU first and then send the data to GPU. And then we have another CUDA flow writing a kernel based on GPU to find the k centroid, to find a k cluster at each iteration. And we have another CUDA flow to send the result back from GPU to CPU when we finish the computation. Because this process is iterative, so we use a condition task to model this control flow. So you can see the entire task graph, there is only a single task graph to describe this iterative control flow. And you don't need to write a task graph, partition a task graph, and with another for loop to synchronize the execution step by step. You don't need to do that. Because in Taskflow, we directly integrate the control flow into task graph. So you can perform end-to-end parallelism. Any questions so far before we move on to the next topic? So we got a question over here. Is it possible to schedule CUDA stream using CUDA flow? The answer to this is no, because we hide the string complexity from you. But it is possible for us to expose an interface for you to give a string to the cont'd flow. Any other question? Because once you are able to describe a GPU workload in a GPU task graph, you don't really need string. The reason you use string is to have concurrency between GPU operation, right? But if you are able to describe this operation in terms of graph, then we can do this scheduling for you. You don't really need to worry about how to insert which operation into which string. All right, so let's move.
What if we have a CUDA flow, but the hardware does not support it? Is that detected somewhere?
Can you repeat the question again? Because your voice is vibrating.
Okay, yeah. If we have a CUDA flow,
yes,
and the hardware, or a GPU flow, and the hardware does not support it, is that detected in some way?
Yes, by default we use CUDA graph. So once you finish the description of a GPU operation using our CUDA flow interface, we automatically transform the CUDA flow into a CUDA graph. And CUDA graph is a very new feature by NVIDIA since the CUDA 10. And the newest GPU architecture, like Ampere, does support this hardware level acceleration for CUDA graph. But yes, we for some architecture they do not support CUDA graph. You need a very new, you need a version of at least 10, CUDA version 10, in order to use CUDA flow. According to our experiment, the CUDA graph has really excellent performance compared to CUDA stream.
Okay, thank you.
Sure. So let's move on. We have learned a core programming model of Taskflow to describe a parallel program using a task dependency graph. And being a C++ developer, not only do we care about the expressivity of the library, we also need performance, and that needs efficient scheduling algorithm. So I'm going to show you our scheduling algorithm and how we can submit a return task flow with control flow into the execution engine executor. An executor is where you submit a task flow to execute tasks defined in that graph. An executor manages a set of worker threads to run task flow. And all the execution methods are non-blocking and thread safe. So you can pretty much do whatever submission you want. Let's take a look at an example. Suppose we have a 3 task flow graph, task flow 1, task flow 2, and task flow 3. And we have an executor. And we define several methods to run a task flow. For example, you can use the method run to run a task flow by once. Or you can use run n to run a task flow by n times. Or run a task flow until the stop predicate becomes true using run until. For example, in this line, I will run task flow by 5 times. In addition to running the task flow, you can launch a task asynchronously using the STL style asynchronous function code. And this makes it very handy if you want to create a task on the fly. And the schedule will autonomously execute all tasks and decide which worker thread to run which task. And finally, you can use this wait for all to wait for all the above tasks to finish as the final synchronization method. And our scheduling algorithm has 2 levels. I'm not going to go into too many details because this is a very huge part of a task flow project. But essentially, it has 2 levels, task level and worker level. At the task level, we decide tasks. We decide how tasks are in queue to the values under control flow. At the worker level, we decide how tasks are executed by which worker. So in order to schedule tasks under control flow, we define 2 dependency types, strong dependency and weak dependency. And the weak dependency is the dependency coming out of a condition task. Others are strong dependency. For example, the dependency from this converge task to output and optimizer are weak dependency. And the task level scheduling flow is as follows. when you submit a task flow, it starts with a task of no dependency, including both strong and weak dependencies. In this case, we will start from this init task because it has no dependencies. And when the scheduler executes a task from the queue, it branches the execution depending on the task type. If it is a condition task, it invokes the callable. If it is a condition task, it invokes a callable and get a return value. And we know the return value indicates the next task for us to run. So it will directly enqueue the successor from that return value into the queue, and then move on to the next iteration. If the task is not a condition task on the other side, then it falls back to the normal scheduling flow for the red acidic graph. For example, they invoke the task callable and then you decrement the strong dependency, because once you finish a task, you resolve the dependency coming out of the task, and then insert all the successor of the task of 0 strong dependencies. And the condition task is very powerful for you to describe control flow in a task graph, but it's very easy to make mistake. And the following example shows some common pitfall of using condition tasks. Again, there are many details on which you can find in our documentation. I'm not able to cover in 1 hour talk, but just want to highlight some common pitfall. In the first graph, we have a condition task A, and it precedes 3 tasks. One is itself, and the other one is B, and the other one is C. And the problem of this graph is it won't get scheduled because there are no tasks for you to start with. Remember, we always need to start with the task of 0 dependency, and there are no such tasks. So to fix the problem, we need to artificially add a source task like S and have the source task to precede A. So we can start with S and then move on to this condition task. And the second pitfall here is you may run into task race. Both E and C, both task E and C are 0 dependency, so they can both start together, right? Now, when E finishes, the scheduler will enqueue task D. At the same time, if the task C returns 0, it may ask the scheduler to enqueue task D again. So we run into this situation of task race. Multiple threads touch the same task. So this is not allowed. In order to fix this, we need to add an auxiliary node between task D and C, such that we can separate this condition by 2 strong cases. And if you look at this diagram, it totally makes sense in a single-threaded control flow, because we won't run task D until both conditions are true, which is E finishes and C returns 0. In the worker level, we adopt the work stealing to run tasks, and work stealing is a masterpiece of work. We have spent a lot of effort, and unfortunately, I won't be able to cover all the detail. But essentially, the idea of work stealing is a dynamic scheduling algorithm. I finish my job first, and when I finish my job, I steal a job from you. So we can improve performance through dynamic load balancing. And when a worker thread drains out its task queue, and it tries to get some more tasks from other worker. And there's an excellent talk about work stealing at CPPCon 2015 by Pablo Halpern from Intel, and you are definitely encouraged to watch it for more detail. And this is just a high-level idea about our work level scheduling. We keep a set of different workers per heterogeneous domain. For example, we have CPU worker to run CPU tasks. We have a GPU worker to run GPU tasks. And we try to balance the number of worker and the available task parallelism. Because when you are running a task graph, the available task parallelism at any time change from time to time, right? So we always need to make sure the number of worker that are running a task is not oversubscribed or underutilized. So we have a spatial strategy to strike a balance between the number of workers running a task and the present available task parallelism. And this is just a slide showing the architecture of our work stealing scheduler. And this slide has a 2 domain, one for CPU worker and the other one for GPU worker. So each domain has a set of workers to run tasks of the same domain, and the worker can only steal tasks of the same domain from the other. And one thing I would like to highlight is in this architecture, our scheduler is generalizable to arbitrary heterogeneous domain. So we have understood the scheduling algorithm in Taskflow. Next, I'm going to present to you some of the results we have obtained from applying Taskflow to real application. And this performance data is another big thing we really care about. The first example I'm showing here is a micro benchmark, and the purpose of micro benchmark is to demonstrate the pure tasking performance without too much bias on application performance. And here we randomly generate a task graph with even CPU GPU tasks and does some nominal computation because we don't want to be biased by application algorithm. And we compare Taskflow with 4 popular parallel programming library, TPP, StarPU, HPEC, and OpenMP. And here you can see from the table one here, the programming cost. And in terms of the lines of code and number of token and cyclomatic complexity for the code, Taskflow always has the least cost compared to the other. And in terms of the graph creation overhead, Taskflow is also the least. For example, in order to create a task, it takes about 61 nanoseconds, but it would be 99 nanoseconds for TPP and more than 200 nanoseconds for StarPU. And this is the performance of running the benchmark. And blue line is Taskflow. Red line is TPP, light blue is StarPU, and black is HPEC. And you can see from this figure where we show the runtime, Taskflow is faster than the others. But in terms of memory, Taskflow is a little bit higher than the others because our scheduling maintains separate data structure for each domain, and that gives us some memory costs. In terms of energy consumption, you can see we have the lowest, we are the most power efficient. We can finish the workload in the fastest time using the lowest energy. And the second experiment I'm going to demonstrate is the real application of machine learning, where we try to compute the inference of a very large deep neural network. It has up to 50 gigabytes of memory if you do not run it in parallel. And this is also the problem given by the HPEC High Performance and Extreme Computing Conference as their yearly graph challenge problem. And the figure here is a partial Taskflow graph of 4 CUDA flow. And you can see there are 6 static tasks, 8 condition tasks to describe the iterative machine learning workload. Each CUDA flow contains thousands of GPU tasks. If you launch this GPU operation one by one, the overhead becomes very significant. And because this network is very large, so the advantage of task graph parallelism starts to come out. Again, we implement this algorithm and compare our performance with TPP and StarPU. And you can see in terms of the runtime, Taskflow is the fastest, achieve the best runtime. It's much faster than TPP and StarPU, about 2x faster. And memory consumption is also about 1.6x less because the use of condition tasking. We are able to describe the iterative control flow using condition tasks instead of unrolling the task graph across iteration. So I would like to summarize this result with the following takeaway. A parallel programming infrastructure is just important as the parallel solution itself. Different models are going to give you different implementation. The parallel code or algorithm itself may run very fast, but the parallel computing infrastructure you use to support that algorithm may dominate entire performance. And this is especially important when you consider heterogeneous workload, because control flow decision always happen at the boundary between CPU and GPU tasks. If you do not have an interface that allows you to describe these CPU-GPU dependent tasks along with control flow, the overhead to partition or synchronize your parallelism is going to outweigh your performance benefit. So far, we have seen a performance of Taskflow in real application. We talk about micro benchmark and large-scale machine learning problem. Now, I'm going to share with you some of the experience we have learned from using C++ to handle large-scale parallel application. And hopefully, our experience can contribute to the community so we can make C++ more amenable to parallelism. Parallel computing is never standalone. It beats nothing if it doesn't apply. No one will buy the parallel computing tool without application. So we must always bring parallelism to practice and apply it to to application. And given a tremendous application, I don't believe a single model or API can express all the parallelism. We need multiple CPP experts in parallel computing because each of them has expert in certain application. For example, we cannot rely on a super powerful language or compiler to parallelize everything for us. Otherwise, the scalability becomes an issue. On the other hand, we cannot rely on heroic programmer or super programmer, ask them to do everything such as scheduling, concurrency control, and workload partition. They are not difficult to program correctly. We do not have a CPP man in a Marvel series, right? And we need library runtime model to assist a developer with parallelization detail. And here is how I think about the current status of C++ parallelism as an existing tool. For me, C++ parallelism is still very primitive. We have stu thread. It's very powerful, but it's very low level. You can use the stu async to launch a task asynchronously, but there's no way for you to describe dependency, right? Which turns out to be more important. There are no easy way to describe control flow in parallelism. If you look at the C++ 17 parallel STL, the only possible parallel infrastructure you may use is box synchronous parallelism. You run something sequential, and then you run something in parallel, and then you synchronize everything, and then you repeat the flow again and again. Also, there are no standard way to offload tasks to accelerators such as GPU. Of course, there are many existing third-party tools that have enabled a vast success in parallel computing over the past year, but there are, for me, the biggest problem is they lack an easy and express interface for describing parallelism. They can achieve by modern C++. There are no efficient mechanism for modeling control flow, and most of the libraries are based on diversity graph, and they do not allow you to describe cycle, which is very important for iterative workload. And when control flow happens, it goes back to sequential flow. All right, so to sum up, we have presented Taskflow as a general purpose parallel tasking tool. It introduces a simple, efficient, and transparent tasking model. We also talk about the general idea about our heterogeneous work state executor and demonstrate its promising performance in large-scale machine learning and micro-benchmark. There are many excellent efforts from the C++ community on parallelism. Taskflow is not to replace anyone, but to complement the current state of the art and address their limitation on the task graph parallelism by using the power of modern C++. And we are very open to collaboration. We believe collaborative effort is the only way to make C++ amenable to parallel computing. Right now, we are based on CUDA, NVIDIA CUDA for GPU testing, but we definitely want to integrate OpenCL, SQL, or Intel DPCPP, and so on. And we want to provide more high-level algorithm on top of our task graph. For example, C++ 17 parallel algorithm on top of Taskflow. If you ever use Taskflow, please let us know. We want to learn from you, and we can broaden our real use cases. We'd like to take this a chance to say thank you to all the users. There are quite a few people using Taskflow right now, and I'm very grateful for the tremendously useful feedback from the user. Again, I'm very open to collaboration, whether you are interested in using Taskflow, understanding more technical details, or getting me to talk about how we can make C++ more amenable to heterogeneous parallelism. Feel free to email me, and this is my information. And you can also find out more detail about the Taskflow project at this GitHub link. With that, I'm going to cut here, and thank you very much for your participation. So I'd be very happy to take any questions.
Hello, this is Shivan here. So thank you for your interesting talk. So how does Taskflow and executor proposal. There's a executor's proposal, right? In the for the standard, how do they interoperate, or are they going to interoperate? Will they be interoperable?
Yeah, so the question is, how does the executor in Taskflow interact with the executor proposal in C++? And the short answer is, if you look at the executor proposal in C++, it is task-based. It is not task graph-based. The executor defined in Taskflow, essentially we require you to give us a task graph. So you describe your application in terms of tasks and related dependency between tasks. But in CPP proposal, the executor proposal, it does not allow you to define the dependency between tasks. It simply launches a task you define. So you cannot do any dependency between these tasks. And that is the main difference between our executor interface and CPP interface. And I would say the community is trying to get everything together into the single executor in the C++ standard library. For example, you can create an async task, a synchronous task, and run it on the executor. And then you can also create a networking task and run the networking task on the executor. So they are trying to make everything unified into this executor. And I just don't know how that will happen in the future. But at least based on my experience, it will be very difficult to have everything, because you think about that, each task has unique property. How can you execute a task that is I/O bound with another task that is more CPU bound together, right? And you always need to come up with a different scheduling strategy. So I just don't know how that will look. I know the entire community trying to push a lot of effort to unify everything into the single executor in a C++ proposal. But in Taskflow, we focus more on tasking. So we want you to describe a application in terms of task graph, and then you give me that task graph, and we do this computation for you and scheduling.
Okay, thank you.
Sure. Yeah, executor is a big part. Lots of people, it has been there for probably 10 years. But yeah, some people say it will show up very soon in C++ 23. But I just don't know how it will look.
Not really sure of that actually.
Yes.
So Dr. Yuan, is it possible to create copies of the task graph?
You mean copy the entire task graph?
Yes, the task graphs. Yes.
It is possible, but right now we do not allow users to do that, because in the scheduling we do maintain a lot of soft mapping, so we keep reference to the running metadata to save memory. The best way to copy the task flow graph is to just recreate a task flow with the same topology.
Yeah, that's something which I had observed when I viewed your library for considering for one of our projects. So I would love to describe my entire flow in a graph, in a task flow, and reuse it, relaunch it every time I strike a situation or something like that, instead of having to create.
If you want to reuse a task flow, then you can use the run method from the executor, because executor provide several methods for you to run task flow in various strategies. For example, you can run a task flow by multiple times, or you can run a task flow based on a given predicate, or you can do some customization.
Okay, running it on a predicate is sounds
yes,
good, actually.
And more
you
important,
have to wait for an event.
Yes, and more importantly, you can use condition tags to manipulate this iterative control flow. And the reason why based on my experience and the reason why people want to partition this task flow and let each partition represent a particular part of their program is because they meet control flow. But in task flow, we allow you to describe control flow, integrate control flow directly into the task graph. So you don't need to partition your task graph across control flow decision. So I remember during the CPP conference, and the Herb Sauter mentioned, if you look at a parallel library defined in C++, you have this asynchronous function call. You can launch a function asynchronously and throw it into a different thread. It's fine, but once you reach a control flow, oops, you have to synchronize everything, right? For example, you have a for loop, and you in each iteration you spawn a asynchronous task, but once you reach control flow, somehow you need to synchronize all the tasks. But in task flow, we have a special condition task interface for you to integrate control flow into the graph entity, so we can describe the entire parallel workload using end-to-end parallelism.
Okay, thank you very much.
Oh, yes.
Any more questions?
Yes.
I think Dr. Huang, now no one has any question. So we can proceed. Can you stop sharing? Yeah.
Let me stop sharing.
Thank you.
Thank you, community.
Thank you very much, Dr. Huang. It was a very insightful and knowledge-gaining discussion. It's a very interesting thing you're going here.
Thank you so much.
Thank you, Dr. Tsung-Wei, for this wonderful session, and thank you everyone for joining this session. And I hope everyone have learned something new today. And we have shared one feedback form in the chat section. Please fill that form. It will help us to improve. And if you joined this session directly through Meet link and still not registered with the community, please register. That link is also in that chat window. And if you have any question, you can post us. You can ask on our Discord channel. You can mail us. So that's all.